Seaberg. He's a student in the magnetics group. He's been there for a while. Not enough to go quickly. But so advanced, he hasn't suffered enough. As an advanced graduate student, it has a full hour presentation here, so thank you.
Thanks, Raphael. As I said, my name is Matt Seaberg. I work in Margaret and Henry's group, and I'm happy to be here to give the COSI seminar today. So I'm going to be talking about high-resolution imaging using UV light and soft X-rays generated from high-magnetic sources. So just a bit of an outline, I'd like to start by giving an introduction to X-ray microscopy, then talk about the type of microscopy that I work on, which uses coherent X-ray sources. Then I'll tell you about our recent work where we obtained 22 nanometer resolution of a fixed sample, and then how we can extend that to obtain some 3D information from the data that we take. And finally, some of the future goals that we have, and also including some extensions of this type of imaging. So I'm going to start with the introduction. So why would you want to use soft X-rays? So there's several reasons why soft X-rays are just a great way to probe things on the nanoscale. That includes the fact that the wavelength is on the scale of 1 to 10 nanometers. And so basically any imaging system that you have is, if you want to do traditional imaging, you need that basically your resolution is set by both the numerical aperture and the wavelength. Another nice thing about X-rays is that as opposed to electrons, they have the ability to penetrate thick objects because they're not as strongly interacting with matter. And finally, they also have elemental and chemical specificity due to the fact that basically different atoms and materials have absorption edges at different regions of the X-ray spectrum. So basically you can pick an element that you're interested in and find the photon energy that you need, and that's how you'll find your contrast. So an example of that is what we call the water window, which is in between the carbon absorption edge and the oxygen absorption edge. So basically what happens there is carbon is very absorbing, whereas water is relatively transparent. So that allows us to actually look at biological cells and other biological systems. So I just want to provide a brief comparison between like visible super resolution microscopy and X-ray microscopy. They're actually very complementary approaches, because whereas visible microscopies can also reach down to 10 nanometer resolution, it's a very different type of resolution. It's where you're like localizing something small to within certain precision, whereas in electron microscopy or X-ray microscopy, you actually have that's sort of your feature side or feature resolution, and so there's a lot of different trade-offs between these wavelength regimes. So just to kind of illustrate that, this is a fluorescence image using visible light, and then that can actually be refined using a technique called storm, where you have something sparsely emitting photons, and over the course of seconds you can build up an image like this, where you can actually localize the position of these tubes down to 10 nanometers. And then in contrast with X-ray microscopy, you can, so it's sort of, you pick your approach based on what you want to find out. And so for things like structural properties of, say, a cell, X-ray microscopy might be more well suited for that, because you can actually look at the shapes of the internal features, for instance. whereas it's also much more of a pain to work with because you have to do everything in vacuum. You can't have live cells, things like this. So there's just trade-offs to it, and they're very complementary approaches. So to start out talking about X-ray imaging, I want to just kind of provide you with the different approaches that you can use. So in the traditional sense, if you want to form an image on a camera, you need some sort of imaging element in between your sample and your detector. And sort of the two options for that with soft X-rays are either a zone plate or reflective curved mirror. And so the nice thing about a zone plate is it works almost exactly like a lens by basically diffracting light as it scatters through these rings to a point. And so you can use that as an imaging optic. But sort of the limitation of this is that whatever resolution you want to get of whatever sample you're looking at is limited by how well you can fabricate that zone plate. So basically, however small this you can make this outer ring is what sets your resolution. It's almost one-to-one relationship. And then the other thing about curved mirrors is they're never quite as good to image with because it's very hard to get a high numerical aperture. So the other thing about zone plates is they're only usually around 10% transparent in this regional spectrum. But that being said, heroic efforts have been made to make these zone plates with 15 nanometer outer zone widths so that it's actually made possible images such as this where you have 15 nanometer features resolved in a microscope. And as well, so this is at a synchrotron, which is sort of a football field size facility that has several beam lines, costs billions of dollars, and is very expensive to get beam time on. You might have time on a beam for about a week a year. And then on the other hand, you can have your own source in the lab. And this is just an example of soft X-ray zone plate microscopy at some of our collaborators' lab at CSU, where they have an actual 13 nanometer laser. So clearly, this type of thing works. There's a lot of drawbacks though, because you have to have extremely critical alignment between your sample, your zone plate, and your detector when you're doing such high resolution microscopy. So that kind of brings me into what I'm going to talk about next. And that's what we do in our lab, which is called lensless coherent diffractive imaging. And so this is sort of an alternative approach where you don't actually need any optical elements between your sample and your detector. And so I just want to point out that this is the original paper that predicted this would be possible about a little over 50 years ago, and it fit onto one PowerPoint slide. So it's a very simple idea. And the idea is basically that if you can measure some scatter pattern and oversample it by 2 times or more the Nyquist frequency, then you should actually be able to retrieve an image of the object that's scattering that light, even if you don't have phase information. So just some of the advantages before I really get into how this works. Like I said, we don't have any optics in between the sample and the CCD, so you're not introducing any extra aberrations into the system. So in theory, we're diffraction limited to basically the wavelength and resolution. And because of sort of the properties of soft X-rays, we have the ability to image thick samples. We have the elemental contrast. And the other nice thing about this approach is that it's very much more robust to any types of vibrations in the system compared to zone plate microscopy, because basically what we're measuring is this diffraction pattern, which any feature size on the pattern is sort of, it's set by whatever distance you put the CCD away or how small your pixels are. So really we need something like 10 micron, less than 10 microns of vibration in general. But so the sort of the requirements of this technique is that you need a very coherent beam of light, basically like a laser. Incoherent light doesn't work at all. And you also need a sample which is isolated, which kind of relates to this oversampling thing, which I'll get into more. So I'm going to be talking about a lot about sort of light propagation, and so I just want to give you an idea of what type of signal we're measuring. So say we have a sort of a sample like this. This is just a test pattern. What the light that's scattered from that pattern looks like as it moves further and further away. Starts out looking like near field diffraction, which is sort of defined by the Fresnel integral, which is an approximation to the Kirchhoff diffraction integral. But as you move further and further away, you get into what's called the far field, where the light that you're measuring, or the intensity pattern that you see, is directly proportional to the Fourier transform of whatever's scattering the light. So that's what we're typically interested in, is measuring some scatter pattern in the far field, which is directly related to the sample by a Fourier transform. But unless you do something which retains phase information, such as holography, which is somewhat limited in this regime because we don't have good beam splitters or things like this, then we lose all the phase information. And so we need to get it back somehow. And so just to stress how important the phase information is, just have an illustration where we have these two images of a skull and an alien. We take their Fourier transforms, take the phase of those Fourier transforms and swap them with amplitudes, then Fourier transform back, and what comes through is basically whichever one has the phase of whatever object. So it's really important that we can retrieve that phase. So this is kind of the schematic of how we do retrieve the phase, and this is, and what I was talking about in terms of oversampling before, that means that more or less we have 4 more pixels per fringe in this intensity pattern, and what that corresponds to is basically an isolated sample in the image space. And so if you don't have an isolated sample and there's stuff out here, then you're not going to be oversampling your pattern, and you're not going to be able to retrieve the phase. And so basically, the way that we do it practically is we measure this intensity pattern, which must be oversampled. Then we don't know the phase yet, so we apply some guess. There's actually certain ways that can give you a good guess, or you can just apply a random phase, and the algorithm still usually works. So you start out by taking a Fourier transform, and you get something that will probably look much less like the object than this. And then we apply what we know, that the sample is isolated and basically restricted to some size spatially. And what we do is we do something called a support constraint, where we set everything outside the object to 0, or there are also some other algorithms which actually work better, where you sort of subtract what's already there by some fractional amount. Then we apply that constraint. We have our new guess. We do another Fourier transform back to frequency space, and that gives us something where now we have some phase information, but the amplitude information doesn't exactly match what we measured. So then what we do is we take that phase information, keep that, and apply the amplitude that we actually measured. And we just go through this cycle around a couple hundred times, and then as long as we have good nice diffraction patterns, then we'll in general retrieve an image. And so since I was talking about oversampling and the far field, I just want to sort of define in terms of parameters what that means. So in order to get an oversampling ratio that's large enough, in general what we do is we just put the CCD a little further away from the sample, and so that's what this Z distance means. And for shorter and shorter wavelengths, we need to go further and further away because light diffracts less and less as you go to shorter wavelengths. But if you have really small pixels on your detector, then you don't have to go quite as far away because basically you can resolve those fringes. And then the D is just the overall size of the sample, and that kind of sets what angle the rays will diffract from the sample at. And then the far field condition I was talking about is just how far away you have to go so that what you measure is the Fourier transform of the object. And that's not actually an actual requirement for doing this type of imaging. As long as you know how to get back and forth between the two planes, you don't really need to go far enough to satisfy this requirement. The most important thing is to be properly oversampled. And so this kind of sets what kind of resolution we can get based on, because of the fact that we have a finite size of our camera, so that distance away that we have to go kind of sets the numerical aperture of the system. So now, kind of describe what kind of source we need to do this type of imaging. So I want to tell you the exact source that we're getting.
What is the practical sampling factor that you use?
We use usually 4 or more because basically we're limited by the noise in our patterns. So the type of source that we use is basically we generate these coherent X-rays by focusing an ultra-fast, ultra-short laser pulse into a noble gas. And the way that works is, as we focus this intense pulse into the noble gas, the intensity is actually high enough to rip electrons out of a noble gas atom, which then we have this electron propagating in free space, but it sees this very intense laser field, and it actually accelerates away from the atom, but then when the field switches signs, it accelerates back towards the atom, and there's some chance that it's going to recollide with the atom. And because it's been accelerating in this light field, it actually gains energy on its way back to the atom, and that energy is released as a photon that's some harmonic order of the fundamental laser light. And the maximum photon you can generate is sort of set by the intensity of your laser and also the wavelength of the driving laser light. But what's very important to us is that we have the spatial coherence properties of a laser, like I was saying. And the way that we accomplish that is we actually pressurize a hollow core waveguide with the noble gas. And this hollow core fiber acts as a waveguide for our driving laser so that we can keep that small spot intensity over long distances. And then what we can actually do is phase match the laser light with the X-ray light. And what that results in is the coherent addition of the X-ray fields that are generated. And which basically, now we have this large phase matched source which has very, very nice spatial properties. And so we can demonstrate the spatial coherence by doing double slit measurements, and we see full fringe visibility with 2 pinholes. So basically that means you have nice spatially coherent light. And so this is just some first work towards the water window where we're trying to push that wavelength down to where it's useful for biological imaging. So then finally, the other nice thing about this type of source is that it's very compact compared to the synchrotron. You can put it on a single optical table. So we start with the ultrafast laser, and that's actually the biggest part of the source. And then the actual waveguide where the X-rays are generated is this short little 5-centimeter fiber. So now I'm going to go into our recent results, and I just want to describe our particular setup. It's pretty straightforward. We have the laser light focused into the waveguide where we generate our X-rays. Then, because it's not a very efficient process, it's something like 10 to the minus 5. We have way more laser light left over than X-ray light, and in order to do anything useful with the X-ray light, we need to get rid of the laser light. So actually one of our sort of more recent sort of improvements to the setup is this rejector mirror, which basically absorbs the bulk of the laser light but reflects most of the X-ray light. But then we're still left with a little bit of red light, so we have some semi-transparent metallic filters which reflect the rest of the laser light and pass about half of the X-ray light. Then what we do is, I should have mentioned, when we phase match that light, there's actually a range of colors that get phase matched with the laser light. So we have several orders of harmonics propagating together. And sort of the typical way that we do this approach, we want a monochromatic illumination. And so then what we have are these two multi-layer mirrors, which it's actually pretty amazing. You can make a 70% reflectivity, 0-degree incidence mirror for 13 nanometer light by having these like 5 to 10 nanometer layer stacks. And we also, so we use these multi-layers to sort of select a single harmonic and also to focus the light down onto the sample and make basically efficient use of all of our photons. So then after the sample, like I said, we don't have any optics in between the sample and the detector, so we just let the light propagate sort of into the Fourier transform, and this is an example of reconstruction of a micron scale object we can obtain. So we started out working mostly at 30 nanometer illumination wavelength. That just turns out to be much easier. The gas that we use is less absorbing of the light that it generates. And so the exciting part about these results is that we showed that we can get pretty close to wavelength resolution reconstructions. And so this is just a test pattern where we have an SEM image here, reconstructed image here, and this is the scatter pattern, and we show about 90 nanometer resolution by just doing a simple line out across the leg of the figure. So now we sort of made this push to shorten the wavelength that we're using for imaging down to 13 nanometers. We still have nice beam qualities, but as I said, it's just, the gas is just much more absorbent, so we have to work harder to kind of keep all the light that we generate. And so recently we've been able to show similar results where we're getting near wavelength resolution of about 22 nanometers of another test pattern. And we've shown that through similar line out, but then we've also sort of confirmed that result by using a tool called the phase retrieval transfer function. And that essentially tells us out to what spatial frequency we can consistently retrieve the phase of the diffraction pattern. And so as you go along, as you go from the center, that corresponds to a higher spatial frequency of the object. So basically, where that sort of cutoff goes to is where we can retrieve the phase consistently to, and that's what our resolution is. And so that agrees very nicely. Basically, this curve goes to 0 around 20 nanometer resolution. And so then if you look at these curves, there's also something else to note where there's actually sort of a knee in the curve, and we interpret that to be basically the minimum feature size of the sample that we're imaging. So there, I mean, if there's nothing in the sample that has smaller features than that, you're not going to get as much of a signal. And so this 100 to 200 nanometer knee is kind of consistent with the size of these slots. And then on the other pattern, we actually have 50 nanometer slots, and that's sort of where the knee occurs here. And I should say that we're also able to reduce the exposure time down to about 30 seconds for these images, and still obtain 25 nanometer resolution, which is a pretty big improvement for what you can do usually with zone plate illumination or with compact sources, basically. And so we're kind of pushing towards being able to do imaging faster, which is kind of will be useful for like the semiconductor industry, where you want to kind of scan over something you recently made and make sure that there aren't any defects. So then I want to kind of tell you about how we extended our data analysis to actually get some 3D information. And this kind of started by a couple of years ago. One of our collaborators at UCLA was reanalyzing some of our data and noticing that basically what we've been doing is something that we call curvature correction, where if you violate the paraxial approximation in sort of what angle that you collect pattern to, you no longer have something that's linear in spatial frequency. It's not actually the Fourier transform of the object. And so to correct for that, we actually sort of scrunch the pattern down and map the intensity that we measure onto something that's linear in spatial frequency. So then we do actually have something corresponding to the Fourier transform of our object. But if we do this, we're actually ignoring some of the information that's in the data, which is that what we're actually seeing here is sort of a slice through the 3D Fourier transform of the object. So there's actually some information about the spatial frequencies and depth of the object as well. And so they started doing some simulations where basically you take a 3D Fourier transform of some object, just take a spherical shell out of that Fourier transform and throw away the rest. And then you can actually pretty faithfully reconstruct the original object, depending on certain limitations. Mostly that it doesn't work well if you have more than a single scattering event per photon. So that corresponds to the Born approximation. So then once that worked in simulation, they took this data that we had taken previously, mapped it onto this spherical shell, and were able to obtain a reconstruction in 3D of this test pattern, which shows us both the thickness of the pattern and also that we had actually taken the data with the object tilted by a few degrees. And so then we've applied this same algorithm to our more recent data, and I guess I should point out that the algorithm is very similar to the regular lensless imaging algorithm, except that we have more unknowns now because we have this shell in the 3D Fourier transform. We still don't have the phase on the shell, but then we need to get the rest of the 3D Fourier transform back as well. And so we were able to see, actually, that was kind of cool, that these smaller slots I was talking about, this is the sample with 50 nanometer slots, they appear in our reconstruction to not actually go all the way through the object, and there's no other way that we could tell that that was the case, because in We also saw again that it's at an angle. And now I just have a brief rotated movie of that sample. And we put this on an ISO surface, so you can sort of only see one intensity value of the pattern. Oops. Okay, so I also want to tell you a bit about how we can extend this type of imaging and how people have already at synchrotrons done some extensions to this type of imaging, and then also what we're planning in the future. So I mentioned how we need this isolated sample, and there are actually ways to get around that and image something on a larger scale. And the way to do that is to basically introduce the isolation by cutting off the beam at some point, so that basically we have some finite illumination. And a normal Gaussian laser beam is not good enough. It doesn't die off quickly enough. But if you put an aperture in the system, say near upstream of the sample, then that actually provides a good enough hard edge that you can use the beam as your isolation. And then what you can do is you can scan around and actually sort of one term for it is keyhole coherent correct imaging. So the beam provides the keyhole that you look through. Then the other thing I mentioned was that you don't actually need to be in the far field as long as you know how to get back and forth between your detector plane and your object plane. So you can do something more near field, or you can use like a curved wavefront, which is effectively the same as being in the near field. And then also it talks about how we generally want monochromatic illumination, but there's a group that actually has extended this technique to be able to use multiple wavelengths, so you don't have to throw away any of the light you're generating. So in this case, they're actually detecting sort of the superposition of all these diffraction patterns, which don't interfere with each other. So it results in sort of a blurring of the fringes. But as long as you have really good knowledge of what your spectrum is, you can actually still retrieve an image of the object. And so another way that would be nice to extend this type of imaging is to be able to image surfaces in reflection mode, because that's really the only way that we could image something like a processor chip or like the magnetic domains in a hard drive. So this is so far the only result inside of synchrotron where they were actually able to do this type of imaging in reflection mode. And they did it in sort of so it's difficult in the first place to sort of define that isolated sample. And so their approach to that was to actually put in a plane close to the sample several pinholes, which basically if you reconstruct the field near the sample, then you can actually do Fresnel propagation back to the sample plane and get an image like this, which is pretty consistent with the SEM image. So we're actually working in our group on more ways to try to attempt this reflection mode imaging. And so I also mentioned at the beginning of the talk that we should be able to get sort of femtosecond time resolution for this imaging system, but the problem is we always run into having enough flux to actually generate an image. And so if we had enough photons in a single shot, then we have enough to get that type of time resolution. And so then what we can do is we'd have some sort of, we'd split our laser beam into both a pump beam and then a beam that generates the harmonics. So then we have a pump and a probe, and we can change the delay between those and see something in a dynamic system such as heat flow or switching of magnetic domains, heat flow and nanostructures. And then we're also looking into how to image plasmas temporally. So we're working on a new laser system which should allow us to generate many more photons per shot, and that's so that we have much higher pulse energy per shot and still at a kilohertz. So we should be able to do sort of things with sort of things that happen periodically also. So then that system will also be useful to generate the X-rays in the water window. So far we've been limited to 10 hertz for our water window source, which isn't actually enough flux to get an image. But as we move to a kilohertz, then we should be able to move into this water window of 3 to 4 nanometer wavelength, where we can actually generate images of biological cells. And so that we've already demonstrated that we can generate these photons. It's just a question of generating more of them. And so this is the type of spectrum that we see coming out of that source. And we can just pick whatever part of the bandwidth that we want. This dip is just due to some carbon film on the gratings in the spectrometer. And so finally, I just want to summarize. We've been able to push down to 22 nanometer resolution with 13 nanometer wavelength light. And in the future, we're going to push towards imaging these dynamic systems, such as magnetic switching, nanoscale heat transport, and the plasma that I mentioned. So basically, I think in the near future, these tabletop microscopes are sort of poised to be able to do nanoscale imaging with femtosecond temporal resolution. We're going to be able to do imaging in a single shot and pushing towards the bioimaging and also the reflective surface imaging. So I just want to thank our funding and all the people who worked on this project, and thanks for your time.
So we'll have time for questions.
Yeah, very exciting work. My question has to do with your reconstruction of the phase. Is this algorithm predicated on the fact that you've got essentially a binary sample? In other words, it's either transmissive or not?
So that makes it easier, and that's most of the types of imaging we've done, but there's no requirement on that. And so we're pushing towards being able to image more sort of transparent samples. And yeah, there's definitely no requirement that it has to be binary.
How do you go about choosing the phase again? I'm not sure if I caught that.
So basically, we can reconstruct the phase by just applying a constraint in each space, the image space and the frequency space. And what that does is sort of it zeroes in on the unique solution.
So it comes up with a phase that's consistent with the amplitude?
Yes, it comes up with a phase that's consistent with both the amplitude and with the overall extent of the object. And that's been proven to be unique up to sort of like a rotation.
You impose only these constraints, no others?
Typically, we don't impose others. In the sort of scanning technique I mentioned briefly, you can also impose additional constraints of basically overlapping sections of the sample.
But in sort of test case, this is only support phase and frequency domain, and that's it.
Yeah.
Okay.
What's a typical sample for your transmission experiments? Metal on
Yeah, it's,
dielectric or on semiconductor?
so for instance, this sample is lithography etched gold on a silicon nitride window.
Can the silicon nitride window be very thick?
It depends sort of what wavelength we're using. Actually, at the 13 nanometer wavelength, it's relatively transparent, so we usually use 100 nanometer thick. If you go to like microns thick, that's
Okay.
possible. I mean, so it also, it definitely depends on, like as you get higher into the soft X-rays, then things are less absorbing.
How thick is the metal?
The metal in this case is, let's see, I want to say it's about 500 nanometers thick. I guess actually in that 3D reconstruction I have, it was 400 nanometers, I think. Yeah, this is 400 nanometers. But that's how far it was etched into, and it actually been slightly bigger.
Okay.
In your new system that you guys are building, I saw you didn't mention like the focal point was like 25 meters.
Yeah, we're actually, I should have updated that. I think we're planning on using more like 5 meters. And that's just sort of set by the pulse energy per pulse, because basically if you focus too tightly with very intense pulse, then you end up over-ionizing the gas and phase matching doesn't work anymore. Yeah.
In this 3D reconstructions, you use just one single measurement, right?
Yeah. And so we'd like to extend this by adding a couple different rotations, or possibly another color, which would give us a different radius shell.
Can you show again the resolution form that you showed?
Oh, sure. Yeah, I didn't really go into that, sorry.
So if I look at O and substitute down there
Yep.
in the resolution, the lambda is cancelled, right? D is cancelled, so I get 1 over delta lambda divided by P lambda. And I don't see the...
And so there's actually a couple different resolution limits. One is set by the size of the detector, and another is set by the actual bandwidth of the source, and which corresponds to how many fringes we can detect. So this one is basically lambda by delta lambda is the number of fringes that we can detect. And so
What fringes?
in the intensity pattern.
Okay.
So basically, if the path length differs by more than that, then we don't have interference anymore. So what that means is, if you have a smaller sample, then basically each fringe corresponds to higher spatial frequency. And yeah, sorry, they're related by.
So what is the resolution limit? Now
Uh,
I know what to say.
I mean, normally, like if we have a very coherent, very heavily coherent source, then we don't really have to worry about this. And in that case, we're sort of, our typical resolution is set by the numerical aperture of the system, which is just lambda divided by the numerical aperture, and that's set by the distance to the CCD as well as the size of the CCD. And so basically, the larger the sample, the lower our resolution limit is, because we have to move the detector further away. But in that case, you can use these scanning techniques to make the isolated region smaller. sampling. And we can't focus our beams down to under a micron.
You use scalar diffraction, correct? Now, if you have those wide angles, and you need to consider the sphere, then the Fourier transform doesn't apply.
Right, it's
Have
more
some correction factor.
There's, it's certainly not exactly the Fourier transform, but I believe that if you actually take into account the z component, then it is the section of the 3D Fourier transform. And so really the only right way to do it, these numerical apertures, is to reconstruct in 3 dimensions. So either if you can get angle RMB to work, or by rotating the sample and collecting patterns at different angles to build up what's inside the 3D Fourier transform.
Does this radiation destroy the sample?
Our radiation does not, but that is a concern in terms of what the ultimate resolution you get to is. And so basically, like, if you have enough photons in a single shot, then you don't really run into the resolution limit, because you can collect the pattern before the sample is destroyed, even if you only look at it once. But yet the limit in terms of the damage threshold for a biological sample is around 10 nanometers, and that's pretty consistent across the spectrum, because if you have shorter wavelength light, it's more damaging to the sample. But with a non-biological system, it's more around the range of 1 nanometer before it's damaged.
What is the polarization?
We use P-polarized light.
So if you change the polarization, will the pattern change?
I don't believe so, because it's a very small correction term. I think we need to get down to like lambda over 2 resolution before we see an effect.
If you change the orientation of your sample, will you have registration problem?
Possibly. I think we'd have to deal with everything that people in tomography do. Yeah.
For your 3D reconstructions, it looked like the actual depths were a few hundred nanometers, and just measurable with a few other techniques. Was that sample actually measured with another technique to verify?
No, it wasn't. And I guess the only one I can think of would be like an AFM. And so that would be definitely interesting to try to confirm that, because we haven't just gone on faith that our construction was.